So while this is being set up, John asked me to say a word or two about myself. So I'm Peter Lindstrom. I'm from Lawrence Livermore National Laboratory, where I work in the Center for Applied Scientific Computing in the data science or data analysis group. I sort of have a scientific visualization background, but over the past 10 years or so, I've been focusing more on data compression, and in particular, the compression of floating point data. So what I'm going to be talking about today is some work that we've been doing over the past year or so. I sort of got inspired by the work that John started here on posits. And we've been working on similar improvements to IEEE, and as well as compressed representations for floating point that you can actually do computations on. So my talk is essentially going to be split in two. The first half is going to be essentially talking about our CoNGA paper, and then I'm going to be talking a little bit more about compressed representations later. So this is joint work with Scott Lloyd and Jeff Hinnier, both at Lawrence Livermore Lab. And what's really motivating this work is this trend, this alarming trend, I should say, in the difference between compute power and memory bandwidth. So if we look at this trend over the past 20, 30 years or so, what we're seeing is that compute has actually gone up by a factor of 1 million or so, whereas memory bandwidth has gone up by only about a factor of 1,000. So there's this sort of widening gap between the two. And as we approach exascale computing, what we're going to see is that most applications are going to be memory bandwidth bound, okay? So data movement really becomes essential in how to reduce that. So when we're talking about data movement in the context of scientific computing, of course, we're talking about shuffling floating point numbers around the memory hierarchy. And for that, we really currently only have two options, right? We either go with IEEE single or double precision. And the problem with this is that for most of our scientific computing applications, single precision is not enough, either because it doesn't have enough precision or because it doesn't have high enough dynamic range, okay? So in IEEE, we really are stuck with whatever exponent size that they chose, right? So there's sort of this tension between what dynamic range you can support in terms of the size of the exponent versus the available precision within the number. And IEEE chose that for us, and that's not really ideal for most applications. So for these reasons, most applications are using, of course, double precision to do their computations. But on the flip side, when you go to double precision, now you're talking about introducing lots and lots of bits. And most of those bits, I will argue, are actually just full of error, okay? Errors come from accumulated round-off, comes from truncation, comes from iteration errors and iterative solvers and so forth. So not only are we computing on these essentially meaningless bits, but we're also spending enormous resources pushing them around memory, okay? So we're using up a lot of power and performance because of this. So I think now's a good time to start looking at alternative representations to this. Posits is one of them. In our paper, we mentioned a few others that we've come up with. But the point here is that I really want to hammer home is that we need to make every bit count, okay? We need to pay more attention to what bits we're going to be pushing around if we're going to do it in the first place. Okay, so most of you are probably familiar with John's work on unims and posits. What I'm showing here is sort of a comparison chart between IEEE and posits. And in terms of data movements, probably what we want to focus on the most here is the exponent, how that's actually being encoded. So for IEEE, we're of course using a fixed length exponent, 8 bits for single and 11 bits for double precision, whereas posits use a variable length representation of the exponents, okay? Another thing that becomes important is that IEEE is pretty wasteful when it comes to representing things like not a number. So for double precision, there are 9 quadrillion different ways to say that a number is not a number, okay? That probably doesn't make too much sense. For posits, we really have just about one way of doing that, unless John has come up with other ways of doing it, I don't know. But it seems more reasonable to do it that way. Another issue with, of course, with IEEE is that we have these nasty overflows that happen. So it's kind of like, rolling a gutter ball in bowling, right? Once you hit that infinity, it sticks around forever. Your computation is pretty much toast at that point. So aside from those differences, posits and IEEE actually share a lot of characteristics. So both of them encode numbers like so. We have a sign bit. We have some way of encoding an exponent. and we have a fraction. So both representations do that. So the main way in which they differ, again, is that IEEE uses a fixed length encoding, a binary encoding of the exponent, whereas posits use, as it turns out, a Golomb-Rice encoding of the exponent. And Golomb-Rice encoding has been used in information theory and in compression for a very long time. Essentially what it amounts to is breaking the exponent down into a binary part and a unary part. Okay, the unary part, which is essentially just a bunch of ones followed by 0, that says, in JAWS terminology, that becomes actually the regime bits, okay? That has something to do with telling you what the magnitude of the number is. So if we look at IEEE single precision, we're going to encode an exponent e as a bit string, as a 1 followed by a bit string x, where x is some number of 7 bits for single precision. The first bit is essentially just a sign of the exponent. But the way that actually gets encoded using IEEE is that we add 1 to x, and that's our exponent. Well, what if the exponent doesn't fit in those 7 bits? What do we do then? Well, we go to double precision, and what we do is that we add 3 more bits, right? If those first 3 bits are 0, 0, 0, then that means that, well, the exponent actually did fit in 7 bits, and we're fine. If not, then we increment and go to 0, 0, 1, and that gives us the next range of exponents and so forth. For posits, it's kind of similar, but we're saying that, well, hey, you know, if x actually already fit in 7 bits, all we need to do is just indicate that by a single 0 bit and say, hey, we don't need any more bits. Well, the next, you know, if that's not quite enough, then we output, or we encode a 1 bit to say that, well, we need to go to the next larger size, right? And if that's not enough, you go to 2 more 1 bits to say that's the next one, and so forth, right? So you build up this sort of unary representation that says, you know, what essentially is the magnitude of this exponent, plus some additional binary bits that follow that. So that's the posit representation versus IEEE double. Sort of parallel to all this work, if you look back, go all the way back to 1975, Peter Elias proposed different ways of encoding large integers. Okay, these come up in, for example, data compression all the time, where you might not know ahead of time how many bits you need. So if you want to encode an arbitrarily large integer, what do? Well, what Elias said is that we're going to write this integer z in terms of some exponent, so 2 to the e, plus some number of residual bits that follow that exponent. And the problem really becomes, you know, encoding this exponent e, which once again could be arbitrarily large if we're talking about an arbitrarily large integer. Okay, so Elias proposed 3 different ways of doing this. He proposed what are called prefix-free codes, which means that any code word is not a prefix of any other code word. Okay? And there are 3 different codes. There's the gamma code, the delta code, and the omega code. And in the Elias gamma code, we encode e simply as the unary representation of the exponent. Okay, so it's e once, followed by 0 bit, and then followed by r. So once we know that we have e 1 bits, we know that we also have e r bits to follow it. And that uniquely encodes any positive integer. All right? Unfortunately, for very large integers, this becomes not so economical because you have lots and lots of 1 bits following a 0 bit. So Elias proposed as a second code, the delta code, where you actually use the gamma code to encode the exponent, okay? Then followed by the residual bits. Then there's also the omega code that is recursive. It actually uses itself to encode the exponent. It's kind of cute, right? So you encode the exponent of the exponent of the exponent and so forth, right? Eventually you reach 1 and you're done, okay? All right, so let's look at this. So this works for positive integers. I think we can agree that we need more than that. So if we're starting with positive integers, we can encode 1, 2, 3, 4, and so forth using this scheme. So in our paper, we generalize this to the rest of the real line, so to speak, right? So the first thing we want to do is that we want to encode rationals in between these integers. Okay, and the way we do that is just the same way that IEEE and posits do it, right? You just append fraction bits to the end of the integer. And you stuff as many of those fraction bits in there as you can if you have a fixed length representation. Then we need to encode what I call the subunitaries, or numbers that are smaller than 1 in magnitude. So between 0 and 1, we also need to encode negative exponents, right? And the way we do that is the same way as we do in posits, right? We use 2's complement representation of the exponent, and that gets us numbers between 0 and 1 also. We need to encode negative numbers as well, and the way we do that is exactly the same way we do it in posits, okay? We use a 2's complement representation of the number itself, okay? So very nice, and that's contrary to IEEE, which uses a sign magnitude representation, which gives you signed zeros and nested things like that. And then we use a 2-bit prefix to tell where are we on the real line, okay? Same thing as posits, okay? Now, this is better visualized, as John introduced, in terms of representing the projective reals. Okay, so we take our real line and we wrap it around to a circle, like so. And we have 4 very special values. We have 0, plus and minus 1, and plus and minus infinity. So you don't have minus infinity and positive infinity, but you have that represented as the single point at infinity. And of course, this works well. So what I'm showing here on the outside are bit strings that are the binary representation of the values that are actually shown on the inside. All right? And at 2 bits of precision, this is what we get. We get those 4 values. And as we go to higher and higher precision, we start introducing new numbers in between those. And in some cases, those are reciprocals of each other. So this is actually the representation for posits with an exponent size of 0, and that turns out to be the same thing as this Elias gamma representation, okay? So we go from 1 as being our largest number, to 2 as being our largest number, to 4, to 8, so we multiply by 2 every time, and we get larger numbers this way, and more precise numbers as well. All right, so this is all great. We can do this with posits, IEEE, and other types. But we want to go beyond that. So we've developed a modular C++ framework that allows you to generate new number types in a very modular manner. So the idea is that there are several different independent concepts here at play. There's how we encode exponents. There's how we handle under and overflow. There's different ways of handling rounding. I'm going to be talking about something that I call fraction maps a little bit later on that tell you, how do you actually map fraction bits to actual values, right? So these are all independent concepts, and we should be able to mix and match and see, what works and what doesn't work, and insert these in applications and run with them and see, how do they actually affect the error. Okay, so we call this framework NumRep. We haven't come up with a catchy name yet, but so far that's our working title. It allows us to unify and represent lots of different number systems, including IEEE posits and all these other ones, using a single framework, okay? So the user can add to this simply by writing new C++ templates that implement new encoding schemes or new fraction maps and what have you, right? This library uses something that we refer to as the arithmetic type that's used for doing the actual computation. So we haven't actually implemented arithmetic using all these new types, but we actually rely on typically IEEE, or in some cases MPFR, arbitrary precision arithmetic. So the user has to specify how you actually do those computations, and then we convert back and forth between them. We use operator overloading to sort of allow you to do arithmetic, math functions, and so forth. And it becomes really easy to just insert this in an existing application, just replace type defs. So instead of float and double, you just throw one of these in there, and ideally the application works just as it did before, right, but with these new types. We support currently 8 through 64-bit types, so we've got available to us. And really what I'm going to be talking about here today is the notion of exponent encoding schemes and as well as fraction maps. All right, but I only have so much time, so I'm actually going to present a much simplified version of this, okay? And really, many of these number representations can be arrived at using 2 very simple rules. One is an extrapolation rule that says that if this is our previously largest number and we want to insert a new number in here to go to 1 more bit of precision, we need a rule for inserting that number between the largest number so far and infinity here at the top, okay? So that's an extrapolation rule. We also need an interpolation rule that says, well, for all these finite numbers, if we want to insert a new number between two finite numbers, how do we do that? So we need an interpolation rule for that. Here at the bottom, what we're going to rely on is simply reciprocation. So if we have an extrapolation rule up here, we're just going to reciprocate that number to get to the next smallest minimum number. So we really only have to worry about these two rules. And, you know, to go from positive to negatives, you just flip the circle horizontally and for reciprocation vertically, right? All right, so the first one is the extrapolation rule. So the idea here is that we're starting with some Fmax, the largest floating point number represented using a p bits of precision. We want to go to p plus 1 bits of precision. Okay, how do we do that? Well, I've written down the simple rules here for the different types that we talked about so far. I've also added unary as sort of a very simple representation. So for unary, if we had an x max previously, to get to the next one, we just add 1. Okay? So we get these sequences of largest integers for increasing precision, so 1, 2, 3, 4, 5, etc. For Elias gamma, the rule is very simple. We just double what the previous Fmax was. So 2, 4, 8, 16, and so forth. For posits with base b, so b here is 2 to the ES in posit terminology, right? Okay. So instead of multiplying by 2, we multiply by this base b. B is a constant, right? So b to the 0, to the first, second, third, fourth, and so forth. For Elias delta, we square the previous number. It's very simple. You still need to bootstrap this process. If you square 1, you get 1, right? So you need to start with something. So we start with 2, right? And then we square and keep going. And then for Elias omega, which has an enormous dynamic range, we take 2 to the power of the previous Fmax, right? So 2 to the 2 to the 4, you know, 2 to the 16, 2 to the 2 to the 16, and so forth. So we get very, very large numbers very quickly that way. All right, so that's our extrapolation rule, very simple. For interpolation, it turns out that we can also use something that's very simple for most of these existing types that I've talked about so far. We have this simple rule right here, where we have two values, a and b. We want to insert a new number in between a and b. And what we do is that we just take the mean of those as long as a and b don't differ by more than a factor of 2. Otherwise, we take the logarithm of a and b, and then we recursively invoke this rule. And this,
the square root of a times b.
That is the square root of a times b, right down here. But it turns out to be the same thing, right? But this actually generalizes so that if then the logarithms differ by more than a factor of 2, then you invoke this recursively. Okay, so I've given you a few examples down here of how we do this. And for everything but Elias omega, we can get away with just the arithmetic and geometric mean. For omega, we need something that I call hybrid geometric mean, which sort of generalizes beyond that. For logarithmic number systems, or LNS, all we do is a square root everywhere. Okay, so also a very simple rule. So if you want to go out there and implement posits, and John spent a lot of time and his co-workers on this, I guess we'll get to that in the next step. Well, all you need, again, is a generator that does extrapolation and interpolation. So you need to code that up in a class. So we have this simplified framework that's templated on this. So we have these rules that the user or the developer specifies. And then we can get away with just using bisection to implement everything in our framework, okay? We can encode numbers by bracketing them between negative and positive infinity, and then we just bisect these. And every time we go to the lower half, we encode a 0. When we go to the upper half, we encode a 1. And decoding essentially does the opposite. Take a 0 bit, and we go to the left half, otherwise we go to the right half, and so forth. For rounding, all we look at is where's the next bisection point. If we were less than that, then we go to the lower bound, otherwise we go to the upper bound. Okay, so this simplified framework is not very performant. You probably want to do this in hardware, but it's very simple to code up and experiment with. Okay, so here we go. we implement our whole 14-page paper here in just about 200 lines of C++ code. And about 8 or 10 of those lines come from here. So this is the posit implementation right here. This is all you need for posits. Okay, so essentially more or less 2 lines of code. So you have your extrapolation rule and your interpolation rule, and that's it. So that was quite easy. All right, I'm going to switch gears a little bit and talk about some results and comparisons between IEEE and different types. So I want to contrast IEEE and the Elias Delta type right here. So if you're a mathematician, you measure things in units of 1, yay, that's easy. If you're a physicist, you actually have to take real units into account. So if we were to measure the distance to the nearest star, we might say that's 1.3 parsecs, for instance, okay? So in IEEE, we would, of course, use 8 bits of exponent for single precision to represent this. Using Elias Delta, we would need only 2 bits. And as a result, we gained 6 more bits of precision in doing so we get a more accurate answer. Another reasonable way of measuring things would be in light years, right? So we've now gone from 2 bits to 5 bits to represent that. But we're still, more accurate than IEEE using this type. It's not really until you get to something like meters, which is probably not a convenient unit to use for measuring distances to stars. But if you did, you could still do that using both types. In this case, IEEE actually wins, right? It uses a shorter exponent for this. You need more bits using delta. And then if you were really perverse, you would measure things in Planck lengths, which is the shortest distance there is, basically. And if you did that using IEEE, you would say that there was an infinite distance to the nearest star, which of course is not true. So you get an infinite error using that, okay? We simply don't have enough dynamic range to represent that. And using Elias Delta, well, we actually have quite a few more bits left to spare. Okay, what this is a plot that shows you this notion of tapered precision. So what I'm plotting here on the horizontal axis, what the exponent is, and on the vertical axis, what is the effective precision you actually have for that exponent for different number representations. So in all of the subsequent diagrams, I'm going to be using this gray color to indicate IEEE float. So we're saying that we have 23 bits of precision everywhere where you can represent a float. You get to the subnormals down here that gradually take you down to 0 precision. Using these other types, I'm actually going to zoom in on this a little bit. What you're seeing here is that some of these types support as much as 29 bits of precision. So you get 6 more bits of precision over IEEE when the exponent is 0 or near 0. There's no free lunch. There's a trade-off between dynamic range and precision. So if you look at the different posits, you can get a fairly good dynamic range with posits, but then you have to give up precision here in the middle. You can go with lower dynamic range, and then you get all the way up to 29 bits. So that's gamma, or posit 0. You'll see that delta and omega make different trade-offs. They all ensure that you get maximum precision at 0, but they also sort of taper off here and go off pretty far to the right, so you get a high dynamic range also. So most of these types satisfy what's called the universality property. So you need 3 different subproperties for that. You need, first of all, to make sure that each integer is represented by a prefix code. So you have some bit string that uniquely is not a prefix of any other code word or binary representation. You also need to make sure that the representation is monotonically increasing in length. That kind of makes sense. You have larger integers, you need more bits for that. That's easy to satisfy in most cases. And you also need to make sure, this is a little bit trickier, that the length of the integer is order of the actual logarithm of the number that you're trying to represent in terms of number of bits. Okay, so the length, the number of bits that you need can't increase too fast, is all it says. What Elias Delta and Omega have is also what's called the asymptotic optimality property, which means that as you get to bigger and bigger numbers, the number of bits that you need to spend to encode the exponent of that is essentially vanishes. The ratio of that to the actual number of bits that you need for the integer itself, for its binary representation, goes to 0. So that's what this next chart shows here. We're showing here that, so y is in this case, the integer you want to represent. So 2 to the 256 all the way over here. And we're showing here the coding cost, or the ratio between the total number of bits needed to represent that value over just the binary part of that value. So if you could represent it in binary, you would, but binary is not a prefix-free code, unfortunately. Okay, so what we're seeing here is that this is delta and omega, this purple and blue over here. They sort of converge to 1 here, which gives you optimality. So this binary 8 is essentially the same as IEEE with 8 bits of exponent, but with no subnormals. Okay, it also approaches that, but you're stuck there. You can't get to larger values after this, whereas all these other representations allow you to do that if you have enough precision. So posits converge to something that's above 1, so they're not asymptotically optimal. But if you use a large enough ESI, so you can get something that's fairly close to optimal. All right, I'm going to talk about fraction maps. So we've assumed so far that we're going to map things linearly. So we have our number here, and the fraction bits just get mapped to a value by inserting the implicit leading 1 bit before it is the way to think about this. But we can use other transfer functions than just a linear one. So for instance, we might use this one. So what we need to do is we need to map fraction bits. We're going to assume that this fraction lives between 0 and 1, and we're going to map that to 1 and 2. Okay, so 0 needs to map to 1, and 1 needs to map to 2, and things need to increase monotonically in between. But aside from that, we're free to do whatever we want, right? If we use this linear reciprocal map, which also satisfies those properties, and if we use this to map fractions for values that are between 0 and 1, and we use the linear one to map values that are above 1, then you can ensure that you get reciprocal closure. Okay, you don't have to, so unlike in type 2 units, you have a special bit that says, you know, this is a reciprocal of the other number. You automatically get this reciprocal closure. So as long as you choose your subunitary and superunitary maps to be conjugate like this, then you ensure this property, so that's kind of nice. Another map is the exponential one that's used in logarithmic number systems. And for this map, it's actually self-conjugate. Okay, so you have guaranteed reciprocal closure because of this. We suggested another one that's just a linear rational polynomial, and it is also self-conjugate, and it's actually extremely close to the exponential map. So I've actually plotted them here. You can see the red one here is the exponential one, this rational one is the dotted one, and they coincide almost perfectly. You also have the linear one, and then this reciprocal linear one. So to satisfy this conjugacy relationship, you need the map for subunitaries and the map for superunitaries to satisfy this particular equation here. All right, I'm going to talk a little bit about results here. We did a lot of different things in our paper. We have lots of different results here, so I'm going to go over those real quick here. Oops. So I want to first show you some closure plots. So what we're doing here is that we're showing these 2D diagrams. So on the x-axis here, we have one of the operands. On the y-axis, we have the other operand. And we color a pixel white if the sum of those two operands can actually be represented in that number system. And we color it orange or red, you know, if you make a positive error, and then blue if you make a negative error. You see lots of shades of gray here also, which is due to just blending different colors. These were actually computed for 16-bit operands, so those images are like 64K squared. They're pretty large, so they've been downsampled here. But what we're seeing here is that posit 0 does the best of all of them in terms of closure. So for nearly half of all combinations of x and y values, we can actually represent their sum exactly. And the reason for that is that posit 0 are linear between -1 and 1. So they effectively work like integers there, okay? So the sum of two integers is not an integer, so you get closure there. In terms of error, it also does quite well. And then as you go to increasing posit sizes, you get less and less closure. Here's multiplicative closure for these 16-bit operands. What we're seeing here is the logarithmic number system does really well here, which just has a smooth exponential map. And the reason for that is that you essentially, when you take the product of two of those, you're essentially just adding exponents, right? So we get very high closure at 75%. And we compare here to binary phi, which is identical, except it uses this piecewise linear fraction map instead of an exponential one. And you see the closure rate drops all the way down to 0.34%. But that doesn't really paint the whole picture. If you actually look at the errors associated with the products. You're seeing that the errors are actually identical for these two. And you're actually seeing lower errors for some of the posit and Elias types in this case. All right. We did experiments with floating point addition. So on the vertical axis is error. There are different algorithms for summing large sequences of numbers. What we're seeing here is that for sort of the most naive implementations where you just sequentially go through and add the numbers, and also if you first sort them by increasing magnitude, you're seeing that IEEE in gray here does worse than both posits and Elias delta. If you use more sophisticated addition algorithms such as an insertion adder where you always add the two smallest entries and then you insert that into a queue and you keep iterating until you get the total sum, versus the cascade algorithm which recursively adds everything up in a binary tree and Kahan addition. We're seeing that most of these, actually IEEE did quite well in this particular case here. That was interesting to see. But we're seeing that we're essentially down near floating point epsilon in terms of error, so they're all doing quite well at that point. We looked into matrix inversion, so we inverted Hilbert matrices, which are horribly ill-conditioned and really difficult to invert. What we're seeing here is that even for small matrices, the errors creep up fairly quickly. IEEE did worst among all of our types that we tested. The other ones did better. We looked at eigenvalue solvers, and what we're seeing here is that, once again, that IEEE does about 3 orders of magnitude worse than these other representations. In this case, the Elias delta and omega did quite well. What I'm showing here is, I don't know if I'm going to be able to play this. Yes, awesome. So what we're seeing here is actually a shock propagation problem. See if I can start that again. Whoops. That didn't work at all. Let's see that. Let's see if we can play this. So you see this shock that enters and bounces off the wall, and you get things get turbulent and start going well. In the right 3 panels here, we're actually seeing the errors are being visualized here with respect to the double position version. So we're using 32-bit types here on the right. We're seeing the IEEE float did really horribly. Posit 2 did much better, and Elias delta in this case did better than posits. What I'm plotting here is the same error in the density field for this simulation that we ran as a function of time. You're seeing all these different curves. You're seeing these interesting bumps. These correspond to when the shock actually reflects off a wall. It happens again later on. And what we're seeing here is that posits, the orange ones here, did really best here. So this is actually for 64-bit types in this case. So for the 64-bit types, posits did better than delta and some of the other types. Once again, IEEE and binary, which is for all intents equivalent, did far worse. Whoops, sorry. What I'm comparing here is essentially the same thing, except here we're just varying the fraction map that's being used for posit 1 in this case, and comparing that with IEEE. So it's interesting to see that as you change the fraction map from, for instance, this one, we use a linear map for the subunitaries and the reciprocal map for the superunitaries, so we got reciprocal closure in this case. That did almost the best over the entire time domain. The exponential one did quite well. So these are far more, they're not efficient to implement in hardware, but it's interesting to see that we can actually get a fair amount of improvement just by changing the fraction map. All right, so far we talked about how to represent scalars. What about the vectors, matrices, tensors, and so forth? There's actually quite a bit of redundancy out there that we can exploit for that. So what I'm showing here on the bottom left here is actually a 1D line out of a density field from a 3D physics simulation. And what I'm showing here on the bottom is actually the IEEE binary representation of each value that we're seeing up here, okay? So you can see near the bottom here are the least significant bits. There's quite an amount of randomness. I don't suspect that we're going to be able to reduce that in any way, but what we're seeing up here is that there's a lot of redundancy, right? So all of these have essentially the same exponent. They differ by most of 1 in this case, right? So if you were to look at the actual information content here in terms of channel entropy, which I'm showing on the right here, you'll see that there's actually some room here to sort of squeeze out more bits out of this. And that's where data compression comes into play. So I've been working over the years on data compression for floating point data. For this particular 3D field of double precision numbers, the best floating point compressor on the planet gives you about 10% reduction of this if you were to losslessly compress this. That's not very impressive, right? We're not going to be able to do much with that. But if we can allow some loss, then we should be in better shape. And as I said earlier, there's a lot of error in these floating point numbers. We don't need to represent them losslessly. Okay, so this is a similar field that's been compressed by one of my compressors down to 1.27 bits per value. That's quite a lot less than 64 bits, right? Visually, you would not be able to tell the difference between this and the full 64-bit field, okay? Of course, I go to scientists and tell them about this, and they freak out, right? It's like, what are you going to do with my data, okay? So it's kind of interesting that the same scientists are quite used to using data reduction in their workflow, okay? What they do typically is that, well, if they can't save it all, they're going to decimate in time. They're going to save not every single time step of their simulation. They're going to save every 100th or every 1,000th or so, right? They might also decimate in space as well. In climate simulations, it's commonplace to compute averages instead of just decimating, right? The scientists are comfortable converting double precision to single precision before they output to disk, for instance. So they're quite used to this, yet they kind of, they don't like the idea of loss of compression. Well, it turns out that most compressors these days can actually support error tolerances and give you guarantees that we don't introduce too much error. So a few years back, we did an experiment where we looked at, suppose we actually wanted to store the physics simulation state in compressed form in memory and operate it on in compressed form and use lossy compression for that. Would we be able to tell the difference? So what we did is, so I'm sort of showing a cartoon version of one of our simulations here, where in the outer loop, we have 3 main steps. We want to update nodes, update the elements, then compute time constraints, and then we take another time step, and we iterate over this. Sort of an ideal implementation, if we were to use compression with this, so I'm blowing up one of these steps here, is to first decompress a small nugget of data. We want to apply our physics kernel on that data, and then write it back in compressed form, right? That's how we would want to do things. At the time, we did not have a good compressor for doing that, so this is really the approach that we took instead. So we decompressed the entire state at the beginning, then we took the full time step after that, and then we compressed it using a lossy compressor at the end of the time step, and then we iterated. So that was our we cheated, but that's all we had at the time. And what we found was that in most of these simulations, we were able to get away with 4x compression. So instead of 64-bit values, we got roughly the equivalent of 16-bit values. And in terms of the quantities of interest that the physicists were interested in, we saw an error in that final result that was, at most 0.2%. And that was actually quite within the limit of what they were sort of comfortable with. But the problem with this is that the way we implemented things is that we actually increased data movement instead of decreased it, right? We did things that the simulation normally does, plus we did compression and decompression to add to on top of that, right? So really what we need is inline compression, where the compression happens sort of on demand on the fly. So as you access the data, you decompress small chunks of it, right? Bring it into cache, you operate it on it, okay? And then when you're done with it, it gets written back to memory. So we developed a compressor for this that we call ZFP. FP is for floating point. Z is, you got to have a Z if you're doing compression, basically. So it's really inspired by what people have been doing in the graphics community as well as for mobile devices. So on your mobile device today, you actually have hardware texture compression in there that compresses the images on your mobile phone. The way this works is that you divide the image into these small blocks of 4x4 pixels, typically, and you compress all those pixels to a fixed bit budget. Sometimes the user can specify that, sometimes there are sort of hard constraints on it, but the idea is that each block of 4x4 pixels is compressed to the same number of bits. So we generalize that to floating point data. It works the same way. In 3 dimensions, you have 4x4x4 floating point values. They get compressed to a fixed number of bits that your user specifies. So we have a fixed number of bits, so we have random read and write access to values at block granularity, but these blocks are fairly small. The decompression happens on the fly, on demand, as the user makes read and write accesses to arrays. And then we keep a little write-back cache of uncompressed blocks so that we don't have to decompress and compress upon every single array access, right? And we use C++ operator overloading, once again, to sort of hide from the user that all this compression happens under the hood. So the user typically just declares an array, If you're used to declaring an array like so, or using an STL vector, well, now you use this compressed arrays instead, right? You specify how many bits per value you want. The compressor does the rest. These arrays act just like regular arrays, and you don't really know. So just to illustrate my point, here's an example. This is sort of the inner loop of a diffusion code where we used STL vectors on the right. We used these compressed ZFP arrays on the right. You can see that the array declarations are different. The way that we index is also different. We have two-dimensional indexing for two-dimensional arrays. That kind of makes sense. But we do not really need to make these changes. You can also use this bracket notation if you want to. Okay. So those are the lines of code that we had to change to make this possible. This just sort of illustrates that the application thinks that it's interacting with a virtual array. Underneath the hood, there are compressed blocks. There's just software cache in between. All right, so the compressor itself is really composed of 3 distinct steps. We're starting with a floating point array. We perform a block from a floating point array. We perform what's called a block floating point transform, where you represent all the values within the block using a single common exponent. And then all the values are essentially just integers that get scaled by this common floating point exponent. There's an orthogonal block transform that's very similar to the discrete cosine transform that's used in JPEG image compression, but it's actually a lot faster. It involves only addition, subtraction, and bit shifts of integers, so it's very fast. And at the end, we actually, so after the block transform, we have all these coefficients that have lots of leading zeros. So the idea is that if they have many leading zeros, we can compress away those. So we use what's called embedded coding, where we essentially encode the most significant bit of all the values in the block, then the next significant bit, and so on and so forth, until we reach our bit budget. Okay, so that's similar to sort of truncating a floating point number in terms of the error that introduces. We can also keep going until we satisfy an absolute error tolerance, for instance. All right, so here's sort of a synthetic example. So we're starting off with this very nonlinear three-dimensional field that we're going to take those floating point values and we're going to implement a discrete differential operator, the Laplacian operator of this. So it's a sum of second derivatives. So if you inject noise in this, things can go horribly wrong. So these are the IEEE double precision versions of these using 64 bits. This is ZFP and its compressor arrays using only 6 bits. You can see slight differences, but I would argue that those differences are much smaller than what you would get with posits and IEEE half at 16 bits instead of 6 bits. So quite a dramatic difference here. As a matter of fact, ZFP using only 6 bits per value gives you about another decimal digit of accuracy over IEEE floating point using 32 bits. Okay. All right, here's what happens if you want to do finite differences with ZFP. So as is well known, as you go from a grid cell size that gets smaller and smaller, you decrease the truncation error until at some point the round-off error kicks in. Okay, and ZFP arrays don't really have that property. They're almost immune to round-off error, so they just keep essentially going down here until at the bottom here, since we return IEEE double precision numbers from the ZFP compressed array, we can't really do any better than that, but if we support a quad precision, we could do better. Or we could actually compute directly on the compressed representation. All right, some recent work that we've been doing. So far, ZFP uses fixed number of bits per block. That's not ideal. In a physics simulation like this, over large parts of the domain, there's nothing interesting going on. We don't want to waste a lot of bits on that. We want to spend the bits, want to make every bit count, right? So we want to put the bits where they actually matter, which is right around the shock. So let's see if we can get this one to play. Cool. So the coloration here is actually the number of bits per value that we needed to satisfy a 40 bits of precision of mantissa across the domain. So see, I guess I got to go back and I'll play that one more time. So you can see that right around the shock, there's sort of this white band of things. That's where we need the most bits. So we actually need as many as 64 bits to represent that accurately. But over large parts of the domain, we can get away with a far fewer number of bits. So that's pretty cool. So here again, we're comparing IEEE double on the far right. You're not going to be able to visually see any difference between these, so what I'm going to do here is actually show you the error maps. You can see IEEE floats. Lots of error, lots of things going on there. ZFP does better, but compared to ZFP in its new adaptive rate mode, where we're using only 28 bits per value, we're getting on the order of 6 to 7 orders of magnitude improvement over IEEE single precision. And that's also, going back to this plot here, we're plotting the area and the density field over time. And what we're seeing is, once again, that using this new representation, we're almost steadily about 7 orders of magnitude better than IEEE using less storage. All right, I'm at the conclusion of this talk, so I want to say that, you know, these new types that we've seen, posits, as well as the new LIS types, you know, capitalize on the concept of tapered precision to improve accuracy. And it sort of makes this better trade-off between precision and dynamic range. We typically see a wider dynamic range and precision sort of depending on where you are on the real line. You can get more or less precision, right? But you don't have these gutter balls that you end up with in IEEE. And I think our number framework is kind of cool. We're hoping to release this as open source sometime soon. There's a lot of paperwork involved, but I promise I'll get to it one day. It has this nice modular design. You can plug and play. You can implement new exponent encoding schemes and do new things and insert them into your applications and measure things like error and so forth. So it's kind of cool. These nonlinear maps are quite expensive. We probably won't see them in hardware, but I think it's worth investigating, you know, maybe we can use some approximation to these nonlinear maps that's more hardware friendly, because it seems like in many applications they actually do matter. We've seen that posits are almost universally always among the best ones. IEEE are consistently among the worst. Kind of interesting, huh? And we've seen this in lots of different applications. But then again, you know, it's not just about representing scalars. I think we need to exploit the fact also that these scalars are typically very correlated, and there's a lot of room for additional improvements by using these compression over small blocks of values instead of just individual scalars. That doesn't always work, but in those applications it does. It's really worth it because it really, you know, plays on this mantra of, you know, making every single bit count. I'm going to end with this slide and just point out that ZFP, if you want to play with it, it's out there on GitHub. It's actually being developed. It's being funded by the DOE Exascale Computing Project. Go download it, play with it. We're going to have another release in the next day or two. And I think that's all I want to say. So thanks for your attention. Thank you very much. It's like information overload. I'm sorry. Right here.
Alternatives to IEEE, you have like posits and other things. And in the future, we probably will have dark silicon in the chips because like, we have to do something with the transistors. So would it make sense to support all of them instead of just saying, okay, I only want to have IEEE or I only want to have posits? So would it make sense to have a mix of them and then switch between whenever it makes sense?
Yeah, I think so, and I think that's also the plan. I think John's made a point that the chip vendors implement a new version of some numeric type every year or every couple of years or something like that. So I imagine that we'll see, you know, these added just like you've seen support for SSE, AVX, and so forth, right? That there are these new accelerators and new types that are being developed. So yes, I believe that's going to be the case. I mean, I think that hopefully eventually someday, one day, IEEE will die. I mean, I'd be cool with that, but for now, I think that's, you know, yeah.
Okay, thank you so much, and let's applause again. Thank you.
Thank you.